Hello and welcome to lecture number 3 of photo and non-photorealistic rendering. I'm your instructor, as always, Leslie Eisted, and in today's episode we are going to move beyond the discussion of ray casting and start looking at the wonderful world of ray tracing. But just a few notes. First off, make sure you've had an opportunity to take a look at assignment 1, which is now posted. And for those of you who are extra keen on getting things done early, assignment 2 has also been posted. Another thing I'd like to draw your attention to is on Brightspace, you will notice there is a resources section under content. And in that particular section, you will be able to find tutorials for things like Python, extra resources for stuff like radiosity and photon mapping when we get to those particular topics. You'll also be able to find any quick guides that might be helpful in understanding some of this content just a little bit better. So do check that out when you get an opportunity. The other thing that I wanted to point out is that you'll notice that on the course calendar there is a scheduled tutorial and we have not used that slot thus far. How we're going to be using it moving forward is that there's not going to be any formal tutorial session. We are going to use that time as an open question and answer session. So we will open up a Zoom chat, not video, not audio, just text. And you can come into the room if you have a question and I will be there to answer that question. And it's also an opportunity for if you would like a face-to-face video chat, there is a slot there that we can actually use for that. So if you need any help, that's what that time slot's going to be used for. So without further ado, let's actually dive in to today's content. So in our last lecture, we talked all about ray casting. And we did a brief review of things like the dot product, matrix multiplications, affine transformations. We looked at ray object intersections for spheres, but also for triangles. And then we looked at ray casting just in general. And if you remember, ray casting was just the act of sending a ray from the eye or the camera through a pixel in the scene and into the world. And we're just trying to figure out what object is visible from this particular pixel in the image, and that is the color that that pixel will end up being. So it's really just performing this visibility operation. What can I see? I cannot see things that are behind other things. Just what can I actually see? There are no lighting equations that are actually being performed here. We're not saying, well, how well lit is this particular point on the surface that we intersected with? Is it in a shadow? Is it a reflective surface? Is it a shiny surface? We haven't asked any of those questions. We're simply asking, what object did you see? And what color was it? And that's the color of the pixel. When we're talking about ray tracing, we're doing the ray casting, but we're taking it additional steps. We are saying, okay, I see that you have intersected this particular object at this particular point. Now I would actually like you to compute what the color of that pixel is based on the lights and the scene composition. When we're talking about ray tracing, it sounds like we are actually tracing the rays of light. And to some degree that is true, but we're also doing it backwards. Because light doesn't shoot out of our eyes and hit an object and then go towards the light source. Light travels from the light source, hits the object, and then reflects into our eyes. So we're going to trace light in reverse. That's going to let us do a number of really cool effects. And by effects, I mean we're actually going to be able to simulate a fair number of different lighting properties and material properties using this reverse simulation, but there are certain properties of light and reflection and reflective materials that we will not be able to achieve by doing this. And so we will have to introduce other techniques that go in the other direction, such as path tracing, to actually get some of the more realistic lighting. We'll talk about that in lecture number 5. So what we're going to look at today is just the basic ray tracing algorithm. We're also going to look at things like shadows, because that's a really big part of actual ray tracing. And we're also going to take a look at basic materials, things that are diffuse. That means they reflect light equally in all directions. And we will look at objects that are shiny, which is objects that reflect light in specific directions. So we'll be looking at a variety of different things. And then in lecture number 4, we'll look at some of the more complex materials, things that are reflective, things that are transmissive, and so on. So to remind you of the difference between ray casting and ray tracing, because I'm sure you've all seen ray tracing before in the 3D graphics course in 3rd year. We have ray casting is we were just sending, as I said, a ray of light from our camera through the pixel in the image plane and out into the world. And the color of this pixel will end up being the color of the object that we intersected with that was closest to the camera. So it's the first thing that you would hit. That's ray casting. We stop there. We don't go any further. Ray tracing, on the other hand, actually does a bit more work. So we still trace light from the camera through a pixel in the image plane and find out which object we hit first, which would be this orange sphere. The difference here is that now we're going to see what lights would actually be sending light onto this particular point in the surface. So how well lit is this point? Is this point in shadow? So we are going to send additional rays from the point of intersection towards each of the light sources in order to determine whether we are in shadow, and also in order to determine what is the particular contribution of each of the lights to the color of this particular pixel. A bit more work. So we can take a look at the algorithm. So for every pixel P in your image, and remember our image has a width and a height, we're going to create that eye from the eye or the camera, and it's going to go through the pixel P in the scene. Now you might remember from our last lecture that we talked about how the pixel positions are not in world space coordinates, and each of these different things have their own coordinate system. So there's the viewing coordinates, there's the image coordinates, there's the world coordinates, there's the model space coordinate systems, and we need to be able to convert between these. So as part of this process, we are going to take pixel P, which has a 2 component position, just an X and a Y, and we need to find its position in the world space or the view space. And we showed you several approaches to do that in the previous lecture. Once we have found P in the world space, we can now send a ray from the camera through that position, so that will give us the direction. And then we're going to perform a query. We're going to ask, what object in the scene did you intersect first? Now, there could be spheres, there could be triangles, there could be quadrilaterals, there may be many things. But for the moment, in order to figure out which object we've intersected, we are going to need to actually test every single object in the scene. So every triangle, every quad, every sphere, everything has to be tested. Whichever one of those objects is closest to the camera is the one that we're going to be able to see. And so the final step of our algorithm is to compute the color of pixel P. Now this looks almost identical to the ray casting algorithm, except instead of just saying return the color of the object, we now compute the color. And that is because we actually need to do some work to figure out what the color is. So what kinds of things might actually contribute to the color of any given pixel? Well, let's stop thinking of it in terms of the pixel, because the pixel is just a projection of the world onto a plane. What we're really saying is, how is this surface point lit? How do we figure out what color this surface point on this object appears to be? Well, there's a lot of contributions. There is the base color of the object. So for example, just choosing random objects that lie on my desk. Oh look, I have my daughter's hair bow. So we have this pink and white bow. The base color of this object would be pink and white. And the fact that it has a pattern on it means that it actually has a texture. It means it's a pattern. It's not a solidly colored object. So that's going to play a role. We're going to need to figure out, did we intersect at a pink part of the object, or did we intersect at a white part of the object? Then we need to ask questions, is it shiny? It's a bow, it's made of gross green ribbon, it's not shiny. It's not purely diffuse, I would say. It's got a bit of a sheen to it. Definitely not reflective. Like I could put a different colored object beside this and it wouldn't reflect that color, at least not visibly. It's not translucent or transparent. You can't see through it. So that's just describing, the actual object. Then we ask things like, okay, well, now we know what the base color and properties of the material that the object is made out of. Is that the only thing that contributes to the color of the object at that point of intersection? No. Because now we have to ask, what are the lights in the scene? Because the light is going to enable us to see the reflected color off the object. So we have to ask what lights are in my scene. Well, I know you cannot see my lights, but I have one right here, which is a big spotlight, and I have another one down here, which is a small but very bright spotlight, and then I have strip lighting all around the roof of my desk. And today I decided not to use my ring light, but technically there's a ring light right in front of me. So these are all of the lights that are contributing to the color of this. Seeing the color of this object as being this light pink. I guess technically I have a Christmas tree over here too, which is lit. So those are going to contribute. It's not just the fact that they exist. What color are they? How bright are they? How far does the light travel before you can no longer really claim the light is contributing? Lots of interesting questions. Another question is this point on the bow actually visible to all of the various lights? So for example, for the light that I have sitting over here, my small spotlight, if I hide my bow like this, I am occluding the bow from the light. The light can't see the bow, and the bow cannot see the light, which means that light over there is not contributing to the color of this bow. And this bow is sitting in the shadow of my hand. And so that is going to impact the color we compute for various intersection points on this particular object. We're going to need to figure all this stuff out. Now, something you may have been introduced to before, but we're going to go over it again, is something known as the rendering equation. And what the rendering equation does is it's a formula that we use to compute what the color of some point on the surface of an object is as observed from the viewer, i.e. you or the camera that's actually rendering the scene. And it's going to take into consideration all kinds of different things. It's going to take into consideration every light source that's in the scene and all of the properties of those light sources. It's going to take into consideration the properties of the material of the object. And it's also going to take into consideration all of the indirect sources of light. Now, we're not going to worry about indirect sources of light today. That's for lecture 5. Today, we're just worrying about direct lighting. But indirect lighting is the fact that if you had a mirror, the mirror is going to reflect light from a light source onto another surface and cause that other surface to be lit. That is an indirect light source. And when we're talking about properties of the material's reflectance, we're talking about something called the BRDF, and we'll talk more about that another time. So this is what the rendering equation is trying to capture. Now, are we going to do this accurately? Maybe not. Here it is, formally speaking. So you have the rendering equation, which is, you see, a function of 4 specific parameters. Those parameters are the point X, so that is the surface point on the object. This WO here is actually a small omega, but it looks like a W. And that is actually the viewing direction. So what direction are we actually viewing that point X from? And then we have lambda, which is the intensity of that particular wavelength of light that we are observing, and then T is the time at which we make that observation. Now, this rendering equation here is the sum of all light emitted by the object at that point, at that time, at that wavelength, towards the viewer, because some objects emit light, i.e. a light. But there's also things like phosphorescence and fluorescence and things like that. So there are many different objects that actually emit light naturally, other than, like an incandescent light bulb. Plus the contributions of all of the light sources. So all of this Li is all of the incident light, and that is multiplying it by the properties of the surface material and the direction by which we are viewing it. So we're integrating over all of that. Now, interesting things about this rendering equation is that we may not have a precise solution, but we can estimate it, or at least we can estimate or simulate several parts of it. Now, there's some other interesting things about this. When we are ray tracing, we don't usually say, please trace for me this scene at 4:05 in the afternoon. No, we don't do that. That's silly. We say, okay, trace the scene right now. We may have the lighting in the scene set up to represent a specific time of the day, but we don't actually use this time component here, generally. Another thing for the ray tracing we are doing right now is we don't specify a wavelength, because objects will reflect certain wavelengths of light differently. So for example, this bow is reflecting certain wavelengths of light more than other wavelengths of light. So for example, this bow is pink, so it's reflecting a lot more red than any of the other colors. That's why you see the wavelength symbol here, is because the rendering equation realistically should be done according to wavelength. We don't do that. We do things according to the color. So, for example, if we were doing a ray tracer right now, we would use a color as red, green, blue. So the red component, the green component, and the blue component. We would do that. But we're not going to use specific wavelengths. Not to say that you can't. You absolutely could. But we're not going to do that. All right. So if we were to sum up the rendering equation, really all it is it's a way of saying the final color of this point on the surface is the sum of all contributions from all light sources. That's what that's saying. It's the sum of all contributions from all light sources. And our ray tracing is going to approximate this solution by thinking about different ways that a surface might reflect light and different ways that incident light will light that surface, because light doesn't travel forever from something like, you know, a little pen light. A mile away, we can't see that. The equation is also imperfect. So it's a nice idea, but there's a bunch of things it doesn't actually account for. And one of the pretty big ones is transmission, i.e. things like a glass. Light can travel through the glass and it will bend the light actually, and it might even separate the light into separate wavelengths. So the lighting equation does not account for transparent surfaces. Another thing it doesn't account for is something called subsurface scattering. Subsurface scattering is the fact that some materials, such as your skin, even though we perceive them to be opaque, that is, that light doesn't go through it, it's actually not quite accurate. Things like skin, light actually does penetrate the surface and gets reflected not off of the, the actual exterior surface, but from interior surfaces, and it creates the appearance of actual skin. And if you want proof that subsurface scattering actually happens with skin, hold your hand up to a flashlight. Your skin isn't, your flesh is not perfectly opaque. There is what's known as subsurface scattering going on, and when you hold that light up to your hand is going to look red. Your hand's not red. I mean, unless you paint your hand, of course. Which, I'm not sure why you painted your hand. Yeah. All right. Other things that this the rendering equation doesn't really account for are things like polarization. So that's the concept that light can be polarized to a particular direction. Now, you might not be familiar with this directly, but if you've ever gone to a movie and watched for a stereo 3D experience, then you've been exposed to this polarization concept, because how 3D films work in the theater is you put on those what they call passive glasses, and each eye has a filter for a different direction of polarization. So one will only let light in that's directed in a particular way, and the other one will only let it perpendicular to that. It's pretty cool, right? Rendering equation doesn't account for that. And it does have an impact. So if you look at some cameras, you can get a polarization filter. And depending on how you configure the filter, like I have one where you turn it, and if you turn it all the way one way, you will see reflections off the water. And if you turn it all the way the other way, you'll see no reflections, you will see into the water. The rendering equation is not accounting for that. Other things, it doesn't account for fluorescence, it doesn't account for phosphorescence. Now, you could argue that could be accounted for in this emission component, but not really. Right. So we use an approximation of the rendering equation in this course, and that's pretty traditional even in any kind of like ray tracer. We're approximating the rendering equation. We don't have an exact solution. We can't ray trace something so perfectly that nobody could distinguish it. We're not that good yet. We're going to look at some of the basic lighting equations that we use, and those two big ones we want to look at today is something called Lambertian reflectance and another one called Fong reflectance models. And they're all based off of the rendering equation that you see here. And something I want to point out is this lovely diagram, some of the different things that we're going to look at. You're going to need to know that we're using this idea of a viewing ray. That is the ray that goes from the eye to the surface of the object. And then we have a ray that goes from the surface of the object to the light. We have the normal of the surface, which is if this is where you intersect the surface, at this point here, the normal is perpendicular to that position. That means that vector is 90 degrees from that surface. And then we also have reflectance rays, so the direction under which light is reflected, and H we'll talk about later. So let's go back for a moment and try to think about how we would consider what we consider the contribution of a light to be to the color of an object. We're going to start by talking about the absolute simplest of all kinds of light, and that's something called a point light. And a point light is a bright point that emits light equally in all directions. So, I mean, you could kind of think of it like the sun, with one minor exception. The sun actually is big, and it appears in the sky, it's big. In the sky, it's like an area light. It actually has, it's round. It has a size. A point light has no surface. A point light has no volume. It is just a position in space that emits light in all directions. So our point lights have a position, and they also have an intensity. And one of the ways that we could compute the contribution of that light to the surface of our object is to simply multiply the color of the object by the intensity of the light. I mean, it kind of works. But that's not quite correct, because what it didn't take into consideration is the fact that the viewer might be looking at that point from a very strange angle. So they might be able to technically see it, but only in passing. So it's kind of like pulling random objects off my desk here. Let's suppose you have this takeout to soup dip. And I'm looking at this object, and the point of intersection, let's say, is up here at the very top. Now, I can see that point, and how I'm looking at it is from this very oblique angle. And so if the light is up above here, it's making this spot very bright, but I'm down here. So it shouldn't appear as bright to me, because the majority of the light off this surface should be reflecting up and around like that. So this equation here doesn't really work. And that's where we need to look at something called Lambert's cosine law. And what we have here, don't worry about all this integration symbols. We're not going to do any calculus. Is that you've got this point on the surface of the object. The object, we assume, is diffuse, or we say exhibits a Lambertian reflectance. That means that it is going to reflect light equally in all directions. And what we're doing here with this funny diagram is each of these little wedges kind of represents a viewer's position. So you've got at the top, this is where the actual light source is. And the length or area of this wedge is representing how much of that light you would see if you were positioned above that area. So if we were right where the light was, we'd see the most light being reflected to us. It would be the brightest. But as the viewing position moves away and the angle between the incident light and the viewer increases, the amount of light that is reflected is going to decrease. So, the further away we are, the less light we see. So this kind of surface is diffuse, or we call it Lambertian. Smaller angle, greater intensity, and that's between the incident light and the viewing angle. Larger intensity, or larger angle, less intensity from the light, so less bright. We can demonstrate this. What you've got here is I've opened up Houdini and I've put a point light source above this sphere. When I move the point light source, or the object, you'll see that the surface points that are further away from the light, not further away, but they're not, the angle between how we are viewing that point on the surface and the angle between to the light, as that angle increases, the darker it appears. So this is the original position. When I move the light away, even though these points up here can technically see the light, because the angle between the incident light and the viewer is bigger, the intensity of the light is smaller. And that's what gives us part of the shape here too, right? Now, a lot of the time what we're going to do is, it's not necessarily the angle between the light source and the viewing angle. We actually usually use the normal. So, and you can think about it, that actually makes sense here, because I'm actually viewing this looking at the normal. And when this light gets reflected, it's being reflected according to what the shape of the surface is. The viewing angle is involved as well, but we'll talk about that later. So, Lambertian reflectance, here is how we compute it then. So, we have the color of the object. We multiply that by the intensity of the light, and we multiply that by the dot product of the incident light and the surface normal. And that's going to give us the dot product of the incident light and the surface normal is going to give us this angle theta here, so we will know how much of the light is actually being reflected at this point. So when we use that, we have Lambertian reflectance. And it's really easy to do. If you were to open up Houdini, you can, I'm just going to stop that here. We go into our scene view, and I have the material palette down here. There are some very basic diffuse materials down here. So here's a basic diffuse material. And you can see here there's this diffuse reflectivity. We can set that to any value you want. So how much light gets reflected. We can set a base color. There's nothing about this being a shiny or reflective surface because this is reflecting light in all directions. And when we render this, I used a different shader here for this, but this is kind of what you get. The light source is up, actually, over here. You can kind of tell. And you can see here how when we multiply the surface normal of the apple and the surface normal of the candlestick by the angle of the incident light, it's saying, okay, the bigger that difference is, the less light I can see. That makes sense. And the less light that would be reflected back to the viewer potentially. So that's why you see this. All right. That's pretty good. We've got some nice round looking objects now. That's definitely something that we like. I mean, if I wanted to, you know, before we showed you a dragon model, so let's just make a new scene here. Just go to new. We'll put in a ground plane. I like to have ground planes. We showed you a raycast dragon before, and the problem with the raycast dragon was it just said, okay, the dragon has a white material, and that's all I care about. But when we actually ray trace, we want to be able to see the surface shape. And so this is a really big model, so we've got to scale it down a lot so it actually fits. Because I don't want to do a camera. So there's the dragon. Let's do that, and let's put it up. Ta-da. There's the beautiful dragon. And now let's give it a diffuse material, so basic diffuse. And I don't know, dragons are a nice bright shade of red. So now I have this diffuse material. If I raycast this, we just see bright red, which is just the red component beautiful. But when I ray trace this and I use that Lambertian reflectance model, it's still going to be pretty plain, but we'll be able to see the surface shape because we're multiplying the angle of the incident light by the normal. And that's showing us, okay, how much of a contribution the light is actually making to this particular point on the surface. I'm just going to go to render view, just render it really quickly. I know it's not in the view, but you can see here that because of that computation, we can now see the color as it is painted over all of the different scales and fine details of this particular model. It now looks like it has a shape. That's what we wanted. Okay, I better stop this rendering. It's not perfect though, because here's the thing. Lights are not infinite. If I have a light, I don't have any here on my desk. Nope, I don't have any. My kids usually have flashlights all over the house, and normally they're sitting right here, but they're not today. If I have a flashlight, though, the further away I am from the flashlight, the less lit I will be from that flashlight. That makes sense. And as a result, the further away we are from the light, the less of a contribution that light makes to our color. An example of this, and I mean, you could play around with a flashlight. The stars out in the sky, the night sky, there's billions of them out there. And they're all very, very bright, intense sources of, you could consider them point lights. But they don't light up the night. We can see them sparkling there in the sky, but they're not intensely bright down on the earth. They make almost no contribution to each individual one, make such a minuscule contribution to the color of something that we can almost say they don't light up anything at all. So the further away a light is, the less contribution it's going to make. Some proof. So here we have a basic round plane and a point light source, and I'm just going to move the light up. And when I move the light up, wait a minute, it was really, really bright when it was close to the ground plane, and when I moved it up, that brightness is gone. And the brightness is gone because we're further away from the light source. And this particular property of light is actually called attenuation. And it happens because as light travels through a volume, it gets scattered and absorbed by the objects that might be in that volume. And you might be like, but the light's traveling through nothing. How could it possibly be scattered or absorbed? Well, air is not nothing. Air is a material. It's going to scatter light somewhat. And there are very small microscopic particles in the air. There are molecules in the air, like oxygen, and there's water, and there's carbon dioxide, that are going to scatter the light, and they are going to absorb the light. So even though we think of the air as being nothing, it's not nothing. And it can scatter, and it can absorb the light as it travels through it. And that is going to cause a reduction in the intensity of the light. If we wanted to create photorealistic lights, then we need to actually be able to simulate this. Now, in some programs, they will call it attenuation, and in other programs, they call it fall off. And there are various formulas you can use to compute fall off. And we're not even going to say these are accurate. They just look good. The first one is we take the original intensity of the light and we divide it by this r squared term. And the r squared we usually consider to be the distance from the point that we're looking at on the surface of the object and the light source itself. But that formula, even though it's using the conservation of energy law to describe the attenuation, which would be more physically accurate, humans have observed in the ray tracing that doesn't look nice. It's too harsh. It's too strong. What we want is a softer fall off. And so others have used this slight adjustment. So it's the original intensity of the light divided by constant C1 plus C2 times that distance between the light and the surface, plus a constant C3 times the distance between the point on the surface and the light squared. And for some constants that the developer may decide, or they may let you choose what those constants are. And people have found that this results in a less strong, less harsh fall off. Which is nice, right? Which brings us kind of to an interesting discussion point. In the introductory lecture, I wanted to emphasize the difference between photorealistic rendering and physically based rendering. Clearly, there's an overlap between photorealistic and physically based rendering. We want things to look real, and in order to make them look real, we probably should be doing things based on physics. But what we have observed is sometimes we don't need to do the full physical simulation to get a result that looks photoreal. There are many approximations that we can use that give a photoreal result, even though they're not physically accurate. And so we go with that, which is good, because a lot of the time, physically accurate rendering is really, really expensive. All right. So we've talked about the contributions that would be made from a Lambertian surface or a diffuse surface. That is a surface that reflects light equally in all directions. Stuff like the fabric that this dress is made out of, which I actually think is hemp. And it's not shiny, it's not reflective, and if I think about it, it probably reflects light fairly equally in all directions. When we think about like diffuse or Lambertian surfaces, you might be thinking of like paint on a wall that isn't a satin finish, so like a matte finish, or the carpet on the floor. You could probably assume that's a Lambertian surface. Non-shiny fabrics. If you've got a laptop or something like a mouse with that funny coating on it, like a rubberized coating, this is actually a perfect example of like a Lambertian surface. True story. Those reflect light equally in all directions. We can't see any shiny highlights on them. What do I mean by shiny highlights? Well, this would be the one time I have no shiny objects around here. Why do I have no shiny objects? I guess I have some. Okay. Got this little baby toy here. Yeah, yellow's gonna work better. So this object here, this cute little bee on it, is it's this like school bus yellow color. It's not a Lambertian surface. And the reason why it's not a Lambertian surface is because it's actually shiny. And depending on how I hold this, and I know it's kind of getting keyed out here because it's reflecting some of the green from the screen behind me, you can see here there's these white highlights. These white highlights make the object look shiny. This is called specular reflection. And its model of reflectance is different than Lambertian's, because the light isn't being reflected equally in all directions, because if it was, we wouldn't see the shiny white highlight. The fact that we are seeing the shiny white highlight, well, it's reflecting the actual light color itself, which means that it's not reflecting it equally in all directions. We're seeing a more direct reflection from the object. And so now we want to talk about how do you deal with lovely shiny surfaces like this little toy. So first off, when we have a material, if it's a Lambertian material, we'll typically say, here's the color. That's it. Here's the color. It has no specular component, no concept of shininess. It's just, here's the object, ta-da! Here's its color, ta-da! Go from there. For a surface that has specular reflection, we need to also specify how shiny the material is. And we need to also say, what's the specular reflection color? Because it doesn't have to be the color of the object. It can actually be a different color. So that's kind of a fun thing. So to give you an example, here we have this diffuse surface again, and I can make it shiny. So I can set, I can set this to shiny, and when I set it to be a shiny object, now we actually see this white specular highlight. And our brain sees that and it's like, oh, this is a shiny surface. It's reflecting something. Not shiny, shiny. So I want to help you visualize this particular model. So what we have here is 3 different kinds of reflectance. So we have perfect reflection. That is, we have the normal to the surface. The incident light is reflected at an angle that is equal to the angle between the incident light and the normal. So if this is 45 degrees here, then this is 45 degrees here. End of story. Perfect reflection. 100% of the incident light is reflected along that angle there. Then we have diffuse light reflectance, i.e. Lambertian surfaces. With a Lambertian surface, you have the incident light is reflected equally in all directions, or somewhat it gets reflected in all directions, according to Lambert's cosine law. A shiny surface that isn't perfectly reflected is somewhere in the middle, depending on the shininess parameter and how that shininess parameter is used. So when you have a shiny object with some degree of shininess between 0 and 1, which may or may not be scaled depending on which shininess model we are using, we're reflecting light now, not necessarily equally in all directions or according to Lambert's cosine law, but instead of reflecting it like this, maybe now we're reflecting it like this, or along this cone instead of along a line, or, just out like a hemisphere. There are many, many, many different models, lighting models, for shiny surfaces. And not every object or not every material can be created with every single one of these models. So the most popular that you will hear about is Fong and Blin Fong. And in terms of physical accuracy, there's not really a big difference between these two. It's just Blin Fong is a bit faster, computationally. These days, I don't think it matters, for the record. There are other models, because there are many different kinds of shiny surfaces. There's things like anisotropic, which means that it's going to reflect light just a little bit differently. Instead of from a point, maybe it's reflecting it from a line, and things like that. So there's also microfaceting. There's many different ways that light can be reflected from a shiny surface. Metals might be this. Hard plastics that are shiny, like this object right here, very much Fong and blend Fong. I almost feel like they created these to mimic, you know, shiny hard plastics. All right. So let's look at the Fong specular reflection model. So it was invented by this individual here. I'm not sure quite how to say their first name. And it's an empirical model, not a physically accurate model. So it's something that, based on observations or based on evidence, we think this looks pretty similar. We're doing photorealistic rendering, not physically based rendering. So as long as it looks real, and as long as it tricks your viewer, you're good. We don't care how you achieved it. So we have the color of the pixel is the ambient light contribution. Now, we didn't talk about this with the Lambertian reflectance model so much, but what this is there may be a base amount of just light in a scene. There can absolutely be a base amount of light in a scene. Because you're not typically in a room that is perfectly dark with one tiny point source over here. You know, there's some light creeping out from under the door, and the window you can see between the blackout curtains just a tiny bit. Everything wasn't painted in Vanguard black. We use the ambient lighting contribution to estimate the indirect illumination that's present in the space that you're rendering. It is an estimate. It is no means accurate. It doesn't look that good, but it works for now. So that's what it is. So you're multiplying, you're getting the contribution from that. So you multiply like the color of the ambient light by the color of the object. Then we have the diffuse contribution. And you'll see here that this term right here looks just like the Lambert's one, because it is. It absolutely is. It's the same. We're multiplying the intensity of the light by the color of the object, by the dot product of the incident light and the normal of the surface. Now, when we compute the dot product of the incident light and the normal of the surface, we're seeing what's that angle, so we know how much light is actually being reflected along this particular way. What is the contribution from that light source? Plus this new term here, which is a specular contribution term. And what we're trying to do is we're taking the reflected vector, which we compute this way, and we're doing the dot product of that with the view vector. So this is where I said it would come back into play. And then we take that dot product and we take it to the shininess parameter as an exponent. We multiply that by the specular color of the object and the light. So this is the Blin-Fong specular reflection model, and it's fairly simple. Or sorry, did I say Blin-Fong? I meant just Fong. So that was the Fong. The Blin-Fong looks almost identical, and it's a modified version of the Fong lighting model by Jim Blin. It's meant to be a bit faster and more efficient, and the reason for that is you'll see here we still have the same ambient lighting contribution, we still have the same diffuse contribution term, but the dot product in the middle here is this halfway vector H that I said we'd talk about. Let's go all the way back to that picture. There's H right there. It's the halfway point between the view vector and the light, incident light vector. Let's go back to that Blin-Fong page. And we compute H by taking the view vector plus the incident light vector and dividing it by the length of those two added together. So that gives us the halfway point, and we take that to the factor of P. And it gives us a fairly similar result, but it did it with a few less computations. So if you look at R here, we've got vector L plus 2 times the dot product of L dot N times N. So 1, 2, 3, 4 operations. Some of them quite expensive, not that expensive. This one actually has a few less. When these were invented, computers were not as fast. I don't think there's a huge difference these days between these two because computers are so fast now. I mean, admittedly, we're not trying to ray trace on an Apple Watch. Please don't do that. I mean, I've seen weirder things, but don't do that. And if you're sitting there thinking, what weirder things has she seen? I have seen people try to play Unreal Tournament on the LCD panel of a printer. That one still baffles me. All right. So, implementation-wise, the specular term can be achieved by just creating vector H as the normalized vector of L minus V. There's various ways that you can compute the halfway vector. Normalization. What does that mean again? That means that we're making a vector of unit length. The length of the vector is equal to 1. And then we compute the dot product of H and N. And then we just do this little equation here. That's it. Specular color times H to the dot N to the power of the shiny times the light color. Easy peasy. So what does it look like? So again, these are very, very similar. Blend Fong was meant to be a little bit faster, and the fall off of the specular highlight was supposed to be a bit softer, less sharp. So for the same values of P, so the same shininess, you should get a little sharper highlight with Fong than Blend Fong. And I mean, it's not that you can't achieve this look with Blend Fong, you just want to increase the shininess parameter. And again, the reason why Blend Fong came along was simply to make it faster. These are not physically accurate, they are empirical in nature. We were trying to mimic what we saw instead of mimic actual science. Now, if you're wondering, what does my ray tracer do? So I do have a ray tracer. I wrote it 16, 17, 18 years ago. It actually, and if you're wondering, do you still use it? Yes, I do actually still use it. I've made a number of modifications to it over the years. Which one do I use? I actually implement both Fong and Blend Fong, and when you specify materials, you can choose which kind of specular reflection you use. Why not? It's not hard to implement either one. All right, we already kind of talked about ambient lighting, but I want to show you what I mean. So I'm going to go into Houdini here and hopefully not crash everything. Well, first, before we talk about ambient lighting, let's actually make this a shiny surface. So I'm going to put in a different material. I'm still going to make it red. So we'll make it red still. But this one, let's go that down. So, oh no, I do want a roughness parameter. Okay, so if I put that onto the surface and then I render it, probably shouldn't have chosen the dragon model because the dragon model is really big. But you see here, now we've got specular reflection and we've got this nice shiny. And now it looks like a nice piece of hard plastic. It's great. We like it. What I want to show you now is this concept of ambient lighting. Now, we've been using it in the equation as just multiply the color of the object by the color of the ambient light, and that is the ambient contribution. What we're trying to simulate is indirect lighting. We're doing it really badly. So I am going to open a scene. Let's discard that. course, I tried to open something, and it just laughs at me. Cornell Box. Oh, it's laughing at me because I'm looking at the wrong thing. So let's look through camera 1. So this is a famous little scene called the Cornell Box. It's a test scene that was used at Cornell. It's just like a unit cube. We usually put an area light at the top of it. We'll talk more about area lights another day. And then we put some objects in the scene, reflective. And when we want to simulate stuff like global illumination or indirect lighting, we typically do it in a Cornell box because it's nice and easy to do. So if we just use regular ray tracing, which let me make sure I've got regular ray tracing. So I'm going to get rid of this thing here, because we just want regular ray tracing. So we've got this beautiful little toy. So we're going to go to render view, and we'll just render that real quick. There we go. I know it's still going, but don't worry about that. So you can see here we've got this intensely bright red wall and this intensely bright blue wall, and the other walls are white. And we've got this light here. Now, should this really be perfectly black in the shadow? Because that's what we've got here. So what we would normally add here is an ambient light to simulate the fact that there's probably some bouncing of light. So even though this is a diffuse surface, it's still reflecting light, which means that the light reflected from it should be giving some of the other objects that light reflects onto a bit of brightness themselves. But we're not doing that here. So we would use an ambient light to bring that up. I did not mean to zoom in or out. Okay. And some tools, by the way, they'll let you add ambient lights. I see Houdini has one right here. There's an ambient light source. So we could add it to our scene. We could just go ambient light. Let's put an ambient light right here, and we make it really, really dim. Let's make it so that we can see it. We'll make it green, I guess. This is just so you can see what the effect of an ambient light would be. Okay, that one was too bright. So the ambient light was really, really bright. Let's make the ambient light really not bright. Don't make your ambient light super bright. Otherwise, it's as bright as a point source. So I've made it really, really dull. And what you can see here is now the shadowed areas, which would only be truly black if we were in like a room with a point source that was perfectly black. Now you can see they have a bit of a green tint to them. And they have a bit of a green tint because of the ambient light. So there's the ambient light. But that's not really simulating how light would reflect off this wall and then light other parts of the scene. What this should actually look like, I'm going to get rid of the ambient light, and I'm going to drop in, and we'll go into this in more detail, what all I'm doing in the lecture 5. I'm going to add in a global illumination light, and then we're going to go over to render view. This is going to take an extra time because it's doing a lot more work, and it's going to look very grainy because in order to make this work you need to really crank up the settings, and I don't want to do that because it will kill the video capture I'm doing right now. But look at that. This is now doing a more accurate model of the lighting by actually having, you know, the light reflect off the red wall and reflect red light onto the other surfaces. This is what it should look like. This is really expensive to compute, as we're going to find out. And so what that ambient light term does is it gives us a quick and dirty way of doing global illumination without doing global illumination, without modeling indirect lighting. That's what we're doing. And a lot of the time it looks just fine. We will cover global illumination and a much greater detail in lecture number 5, as I've mentioned. But for now, we can just use a basic ambient light. Make sure that your ambient light is a color that actually makes sense. Typically, people just use a really dark gray light. And make sure that the intensity of the light is not very bright, because your shadows should be dark, just not perfectly black. All right. So, what's our final story on the lighting contributions? Well, our final story is that you're going to use for each object a specific model that is for that material. So, for example, I might use Blinn Fong for this shiny plastic toy, and I might use Lambertian for this material on my mouse. Not the buttons, the actual body of the mouse. So we're going to do that. But what if I have multiple lights? So we've just talked about a single light. What if I have multiple lights? Well, if we go back to the rendering equation, it's the sum over all of the lights. So we're going to be doing this for each and every single light, because every light has the potential to contribute color to the scene. Is that enough? No, it's not enough, because we haven't talked about shadows. If you have a light source, you have shadows. You can see right here the shadow of my arm as I move it in front of my face. It's creating a shadow. How do we compute shadows? What role does a shadow play in the final color of the pixel? Well, a light can't contribute to the color of a point on the surface if that surface point is not actually visible to the light, at least a point light. So if I have a point light over here, and then my hand here, anything that is on the other side of my hand, the point light can't see it, and that object can't see the point light. So that point light wouldn't contribute to the color of that point. How do we know, though, if that particular light can be seen by that point on the surface of the object? Well, we're going to have to do a visibility check. Starting from the point of intersection on the surface of the object, going towards the light, we need to ask the question, is there anything on that line? We send a secondary or a shadow ray from the point of intersection on the surface of the object to each individual light source. If there is an object on that ray, that is, it intersects the ray, between the point here and the light source, then that point on this object is in shadow, so that light will not contribute to the color of the object. If, however, you intersect nothing, then the light does contribute to the color of the object. When you're doing this particular computation, it's important to note that you don't have to necessarily intersect all objects. The first intersection you find, you can stop. Because if you're in the shadow of one triangle, does it matter if you're in the shadow of like 16 of them? No. It's not to say it's going to guarantee you improve the performance, but never do any computation unless you have to. So here's a picture of what's going on. Excuse the somewhat silly diagram. What we have is our view ray. So this is our lovely viewer. This is the point of intersection on the surface of the object, and the sun, of course, is the light source. So what we're going to do is the view ray comes in, we compute the point of intersection using the formulas from the last lecture. And then from there, we're going to create a ray that goes from the point of intersection towards the light source. So it's just make another ray. And then we're going to check whether that shadow or secondary ray intersects any of the objects in the scene. So we'll perform a ray object intersection test for each of these objects. You'll note that this ray actually intersects this sphere here, the blue sphere. Therefore, this point is in shadow, and so this light will not contribute anything to the color of this point. That's not too bad, right? A little tiny thing, a tiny detail we'll worry about later, but there is the potential for self-intersection that you didn't mean to due to rounding errors, and this is where those little epsilon values come into handy. You don't want the origin of the shadow ray to actually be the point of intersection. What you actually want to do is move the point of intersection a little bit away from the surface of the object, but just a tiny amount, so that you don't intersect yourself right at the point where you are. It's not to say self-intersection isn't possible. I mean, certainly if you had this object here and the ray was going through here, and so you would intersect yourself. So that's possible. We're just saying if the point of intersection is here on the outside and there's technically nothing between you and the light, you shouldn't be intersecting yourself. So we use that epsilon value. So this is what happens when we add shadows. So you can see here there's one light source that's up over here, and it's casting shadows. So we've got that roundness we get from using the Lambertian reflectance, but we also have actual shadows. So we've got shadows that are appearing on the ground because the ground is being occluded by this object. We also have some self-shadows here because the horse's body is occluding the place where the horse's tail is. So we've got self-shadows going on here as well. And we can add more lights because you're going to remember you need to send a ray from to every single light. Not just to compute its contribution, but to actually check whether it's in shadow or not from each light. And what you end up with is this neat diagram. So you'll notice here the shadow is less intense, and that is because this area is visible to the second light, which is over here, and this area is visible to the first light, which was over here. So it decreases the sharpness of the existing shadows, and you get multiple shadows. And this makes perfect sense because if you actually are in your home and you have multiple light sources and you look at the ground, you know you're going to see several shadows. One shadow for each of the light sources that you're being exposed to. So let's go back and look at another version of our ray tracing algorithms, version 2. This is a much more accurate model. So for each pixel P in image I, we are going to set the color of the pixel to be some initial color. Now I've set it here to black, but traditionally it would be gray. Gray is a really good initial color because it's good for debugging. If it's black, I can't tell if it's just a really bad shadow computation or if I didn't intersect anything. Whereas if it's gray and the pixel ends up black, that's actually informative. So gray or black, it's your choice, but you should probably use gray. We're going to create a ray as before from the eye through the pixel in the image, and we send it out into the world to find out what is the first object you intersect, if any. From that intersection point, assuming we intersected something, we need 3 pieces of information. I need to know the surface point of intersection, I need to know the surface normal at the point of intersection, and I need to know the material of the object at that point of intersection. Because in order to do the lighting contributions, I need to know those 3 things so that I can send secondary rays, so that I can compute Lambertian and specular reflections contributions and know the colors. So I get a point, the normal, and the material. Then for each light L in the scene, I'm going to create a secondary ray, Q, that goes from the surface point to the light. And I'm going to check if Q intersects with any of the objects between the surface point and the light. If yes, then this light does not contribute. If no, I didn't intersect anything, then we are not in shadow of this light. So we compute the light contribution using the surface point, the normal, and the material, and we add it to the pixel color C. So we are summing up over all of the contributions for each and every single light. All right. That's a fun little discussion. So we've got some pretty nice images here, right? I think they're reasonable. I mean, we've got kind of plain things, and then we've got, you know, shiny things like these little toys, hard plastics. We'll get some more realistic stuff later. We'll worry about other materials. Let's look at the cost of this. So we already have evaluated the cost of ray casting. And we knew that was if we have an image that is W pixels wide and H pixels tall, that the number of ray object intersections performed is W times H times N, assuming there are N objects in the scene. Okay. Now that's not an exact computation, but it's a pretty good estimate. Why do we do this anyways? Why do we try to figure out the cost of things like ray tracing? The reason is we like to know how does this algorithm behave, because if we want to improve upon the behavior of the algorithm, how could we possibly improve upon it if we don't know what its behavior is like? How can we understand why the algorithm is slow if we don't know what it behaves like? That's why we do this. And again, I will post a brief guide on this for anyone interested to Brightspace. So now we have a bit more than just our ray casting model of W pixels, WH pixels, and N objects. We also have L lights. And now we have to, for each pixel, in addition to sending the primary ray from the eye to the object, I now also have to send a secondary ray from the object to each light. So for every pixel, for every object, we have the potential of sending another light. So we're going to then account for that in here. So we have W times H times 2N. Because there's the possibility that for each object intersection point, we might be sending another ray for each triangle. And there are L lights, so we might, for each intersection point, we might have to send L additional rays. And that gives us W times H times N times L, which again probably seems really reasonable. Like, those numbers aren't too big. But let's look at the cost of this. So if you had an image that was 1920 by 1080, which is a standard HDTV, and you had, what do we have here? Count the zeros, looks like a billion triangles. Very reasonable by modern standards, actually. And you had 25 light sources. Again, very reasonable if we were trying to create some nice scene. Then we would be doing this giant number here of intersection tests. 5.184 times 10 to the power of 16. It's huge. If each one of those intersection tests took 1 microsecond, which is not a lot of time, this rendering job would take 1,600 years. You wouldn't, and your children wouldn't, and your children's children, none of them would be alive to see the picture you rendered of a red sphere made of a billion triangles. So the problem we have with the cost of ray tracing is just that the numbers are actually really high. So when we say, like, who renders with a billion triangles? Who doesn't render with a billion triangles? That's not necessarily unrealistic. Even if it was 1 million, it's still a really big number. If you're looking at movies, things like Monsters University, which I mentioned before, some of those frames took 29 hours to render. They say that if this was your machine, those frames would take 1,000 years to render. Obviously, Pixar on their render farm are doing a lot of special optimizations to speed this process up. Because this algorithm, this cost, represents a really naive view of ray tracing. Big tools like Houdini, RenderMan, they are doing things to speed this up, and we can speed this up. We'll talk about that. Because it's important to know that you can speed it up. So, ray tracing is expensive because there's just a lot of ray and object intersections happening because there's a lot of pixels, there's a lot of rays, there's a lot of objects. We want to reduce the number of intersections because that is what's causing this extreme cost. Lots of different ways that we can do this. One of the ways that you can do this is with this concept of bounding boxes. So when we talked about intersecting an object, we weren't necessarily talking about there's a formula that describes the surface of this little toy. Let's find the ray object intersection that's a solution to that. What we're actually doing is saying this object is made out of 1 billion different triangles. We want to figure out, do you intersect any of those 1 billion triangles? But here's the problem that we end up having. This object is very small, and if it was made out of 1 billion little triangles and it's sitting, I want to put this right here, over here in the lower corner of the image, why should rays that are going over here try to intersect this object that's clearly nowhere near it? It's a big problem. I'm doing 1 billion intersections on all tests on all these pixels that are nowhere near this tiny little object over here. The idea of a bounding box is we're encapsulating these objects made out of multiple triangles in another shape that's simpler. And then instead of doing the intersection test with each of the triangles that this object is made out of, I'm going to first check, do you intersect the bounding box? So here, this will be the bounding box. Pretend this is a sphere. We're going to put this in the sphere, and then we're going to say, okay, do you intersect the sphere? Oh, you don't intersect the sphere? If you don't intersect the sphere, then there's no point in intersecting any of the little triangles that this is made out of, because you didn't intersect anything with the sphere that encapsulates the object, that bounds it. So we use these bounding boxes, bounding spheres, and bounding volumes to reduce the number of intersection tests performed. So I'm still going to check if you intersect the bounding shape, but I only actually check for the triangles for the object if you intersect the bounding shape. So if the bounding shape is over here with the object inside of it, we'll only ever actually intersect with this yellow object if we intersected with this here. It's a really great way to do it. It's not perfect. The reason why it's not perfect is your scene isn't usually empty, followed by a highly accurate model in the lower left corner. It's usually a world made up of many, many objects, and that actually might be just all one object. It's entirely plausible. So it's very, very possible that the bounding boxes don't necessarily work. Now there's a new technique called, not new, but there's another technique where you use a bounding volume hierarchy, which would be using big bounding volumes with bounding volumes inside and bounding volumes inside and so on and so forth, to try to split the model up into subgroups. That's another technique which is actually much faster. But bounding volumes, the other thing I wanted to say about them is this is actually used in a lot of other places, this concept of a bounding box. Bounding boxes are used for collision detection in video games. Because in a video game, we want real-time performance. 30 frames per second is not good enough. 60 frames per second minimum, which means I need to be testing or doing all of the math behind the scenes as fast as possible. So if I want to check whether this toy intersects this box, and this toy being, let's say, the thing this is your shape, it doesn't make sense for me to check if every single one of these triangles intersects any one of these triangles. It would be much faster if I just said, do the two cylinders intersect? Because if the two cylinders intersect, good enough. The sword hit ya. So we actually use a lot of this bounding box idea in video games for collision detection. It's pretty cool, right? Much cheaper. But imperfect. Another idea is this idea of spatial subdivision. So instead of putting bounding volumes on the models themselves, because we recognize that sometimes the model might be the whole scene, maybe we could divide the space up instead. So rays on the right side of the image don't intersect things that are on the left, and things on the left, rays on the left don't intersect things on the right. So what if we subdivided the space, the world, into regions? And if the ray intersects the region, then we test the ray only against those triangles or objects that are within that region. That kind of makes sense. How does that work? So the first one, and this is an option you'll actually see in many tools like Houdini and Maya, is one, and you might have heard of it in the third year program, is Octrees. And the idea is you're going to take a cube and divide it into 8 smaller cubes. And then you keep recursively subdividing it until each of the little cubes you've subdivided into contains a specific small number of objects, which is typically 1. And you can represent, it's called a tree because you can represent this as a tree. You've got the main world, you divided that into 8 subworlds, and each of those 8 subworlds got divided into 8 more subworlds. So it's a tree, and those are all the branches. And then the idea is that you have a ray, you test it. Does it intersect the world? Okay, it does. Which of the 8 sub-boxes does it intersect? Okay, so it intersected that one and that one. Okay, so we will then only perform ray object intersections with those 2. And then you continue down this. So you're reducing the search space for the ray, which makes a lot of sense. Now, in theory, the height of this tree would be nice to be what we'd say log n, which means so, like if you had 32 objects, the height of the tree would be 5. So you do 5 ray object intersection tests instead of 32. So it's a lot smaller in theory, but the worst case for this particular one is that it didn't actually do any improvements, and that the height of your tree is the same as the number of objects in your scene, so you save nothing. Octrees, they're still definitely used, but I feel like they've fallen out of fashion. So this is that tree structure and then the cube. So you take this cube, you cut it into 8 smaller cubes, and then so long as there are still multiple objects in an individual cube, you just keep subdividing. And this is the tree that would create. It's pretty neat, right? I think it's cool. So it does technically reduce the number of ray object intersections, but it's not a guarantee. It is entirely plausible that you have, and this is a funny one actually, it's entirely possible that your tree has a height of 1,000,000, but you only have 2 objects in your scene. So, I mean, that's not going to happen in practice. It's possible, but who drew a scene that way? It would be weird. Well, how that happens is your 2 objects are squashed together in the like the upper corner like this. And so in order to separate these 2 objects, you have to keep subdividing and subdividing and subdividing and subdividing. Or you've got 1 over here. You actually need 3 to do it. Like you've got 1 in the lower corner and 2 in the upper corners. Gives you a great big tall tree for like 3 things. So in practice it works well, but there's the potential for it to be really bad. But in practice, on average, it does actually work and reduce the number of ray object intersections. So we like these. Can we do better? Of course we can. This is one that Houdini uses specifically, and I'll show it to you in a minute, is called KD trees. And I'm just going to describe these to you. But the idea is, the problem with Octrees was that it can take a really long time to actually get the objects separated so they're each in their own little cube. So you can end up worse off. The idea behind a KD tree is that we want to guarantee that each time we subdivide the space, exactly half of the things are on one side and half on the other. So that we end up truly with log n, which is really nice. So this is a huge improvement, because if you've got this billion objects in your scene, you only end up doing 30 intersection tests. It's huge improvement and massive improvement. And it's a guarantee. So how it works, let's open up a little tool here. Let's get a new, I forgot to save or power up my tablet, so I'm going to draw with a mouse. So here we have a space, and I'm just going to do this in 2D to show you what we're doing. But let's suppose we have some objects in this space. So what we do with the KD tree is we're going to subdivide the space into half, not in terms of half of the image, in terms of half the objects are on one side and half the objects are on the other. So in this case, I have 6 objects, and I'm going to divide like this. Boop. 3 on one side, 3 on the other. Just so happen that looked fairly even. And then what we're going to do is we're going to say, okay, is there only one object on each side? No, so we need to continue this. So then the next time, instead of splitting along, we split along the x-axis, the next time we split along the y-axis. So like this and like this. Now, we weren't, because of the odd numbers of objects, we weren't able to do an even split, but that's okay. And then the next time, this is just x and y, but so you split on x, and then you split on y, and then you split on z. Each time making sure that the number of objects on each side differs by no more than 1. So you're splitting in half. And then the next one, so split here. And then these two are technically on different sides, so we split there. So there we go. That's what we're doing. We're just splitting now on the objects to make sure that each time we split, half of them are on one side, half of them are on the other side. Makes a huge improvement. We love it. There are many other kinds of techniques. There's things called arteries that you'll see. It really, which ones you're going to see depends on the tool that you are using. So in Houdini, and you'll notice I do a lot of Houdini examples. It's because it's the tool I'm most familiar with. It's actually made in Toronto, and it's what I'm using for all the demos in the course. It actually lets you specify which optimization technique you use. And I'll show you where you can find it here. So this is the Render tab, and beside this, you'll see this, it says Out Mantra IPR. That is the renderer I am using, and there's this little menu button here. So you click on that. And then there's lots and lots and lots of options here. And some of these options we'll talk about in the next lecture, but many of these are for improving the accuracy and the rendering quality, the smoothness, and so on and so forth. Which, if you're thinking, if I'm improving the accuracy and the smoothness, does that mean I'm decreasing the performance? Yep, you are. But we need it. So what we're going to do is, I think we click on the Render tab. So rendering up here, render down here. And down here, there is this lovely option called Ray Tracing Accelerator. And I have it set to KD tree because I like KD trees. And the other option, and this is just for the Houdini Apprentice, the other option is bounding volume hierarchy. So that is another approach that they are using that's similar to bounding boxes, except instead of having a singular one, it's actually subdividing the object into more and more bounding volumes. So you can choose between bounding volume hierarchy and KD tree, and I choose KD tree. I have not actually computed a difference. I should actually try that. I'm curious to know which one ends up faster for some of these scenes. That would be fun to try sometime. Not right now, though. I will do this experiment and I'll post the results to Brightspace. Now, this again, so this is Houdini. This is the mantra renderer, and under rendering, render, it's the ray tracing accelerator. And that is just a method for reducing the number of ray object intersections that you're going to perform. And I'm sure Maya and Blender have similar options in them as well. Nobody does them all. Everybody's going to implement something. So a couple other things. So for those of you just want to talk about Houdini a bit more. Houdini is a product that you might have heard of before if you haven't really used it. So far, it is commonly used for particle effects in video games and so on. But it's fully capable, just like Maya. It does, you can create objects in it. So it's got, your polygons, your deformations, your textures. It can do rigging, but it has traditionally been known for its particle effects. So doing things like water, smoke, fire simulations, it's pretty good at. So that's pretty cool. Made in Toronto. But actually, so is Maya. And again, it does a lot of the same things. How you specify materials, how you specify lights, and the how you actually set up the renderer, those are going to be located in different places. And if you need some help with that, please send me an email or go on YouTube, and I'm sure you'll be able to find a great many guides for Maya. It's one of the beautiful things about graphics. There's so many guides online to it, and they're all great. Blender is another open source tool, and these are all ray tracers. Houdini, by the way, can do things other than ray tracing. It can do shader-based rendering. Maya, I believe, as well. Blender is a ray tracer. That is an open source free tool, and I don't think I have it on this machine. No, it wants me to get Blender. I don't use Blender. Everybody kind of has a preference in terms of rendering tools. I have found Maya to be pretty intuitive, and I find Houdini pretty intuitive. I tried to use Blender once many years ago, and I was just like, I have no idea what's going on here. And then I tried to use, I was like, the other day I wanted to do something, and I was like, I'm going to try doing this in Blender. That lasted for about 15 seconds, and then I decided I'm going back to Houdini, and I'll just do it over there. I wanted to render a view frustum. I thought it was a default thing. It was faster to make it work in Houdini than it was in Blender. I know a lot of people love Blender, and it's a great tool. I've just never caught on to it. One that I do use, and I do like actually a fair bit though, is this other free open source tool called Pavre, and it stands for Persistence of Vision. It is very simple, so it's not going to offer a lot of the things that these other tools give you. You really have to have your scene pre-created for Pavre, and it's handled all in code. So this is not like a drag and drop environment. Oh, I'm going to drag this sphere over here. No, it's a programmatic ray tracer. Probably why I like it. But it works really well, and it's fairly simple. So it doesn't have a lot of the fancier features of the other ones, but it's still cool. For this course, for your assignment, so assignment 1, you're going to be implementing some very small components of a ray tracer. For assignment 2 and onward, you are free to choose the tool you want to use. My recommendation to you is use one that you are familiar with already. So if you're an expert at Maya, use it. If you're an expert or you're getting comfortable with Houdini, use that. Don't use this as an opportunity of, oh, Pavre, that sounds very exciting, I should do that. No. Don't do that. Use what you're comfortable with. It's okay. This is not a course about learning to use a specific tool. This is a course about learning how to do the rendering itself and how that rendering actually happens. All right. So that is the end of part 1 of ray tracing. We have another part to come, and in the second part of ray tracing, we are going to talk about textures, texture mapping. We're going to talk about bump mapping, which is a way that we cheat to make a surface look rough, even though it's perfectly smooth. We're going to talk about area lights, volume lights, and just different lights, because right now we've only talked about point lights, but point lights aren't actually a real thing. Lights actually have a volume and an area, so we're going to talk about how you actually do volume and area lights and the side effects of using those particular kinds of lights. We're going to talk about different materials, so things that exhibit subsurface scattering. We are going to talk about reflective surfaces. We are going to talk about transparent surfaces, so things that are going to refract light, like glass. And we're also going to talk about things like improving the rendering quality. And at the end of the next lecture, you should be able to create some scenes that are fairly realistic looking. They're not going to be perfectly realistic because you would still be missing some of the more complex lighting, but they should be pretty realistic at this point. So that is in the next lecture. Then lecture 5, so that's like 2 weeks out, we're going to look at some of the more realistic models of lighting, so the global illumination, radiosity, photon mapping, so getting caustic effects and things like that. So pretty exciting stuff. So there are some review questions here for you to try. They might serve as good review material for the midterm. We will see you later in the live chat and next week for the next lecture.